8.1, the start of acids and bases. We're going to look at the theories of what is an acid and what is a base. Specifically, we're going to be looking at two theories. The first one is the most commonly used, and it's the one we're going to refer to the most throughout the entire unit. It is called the Bronsted-Lowry theory, and I do shorthand it as BL. This is the theory of proton transfer. Therefore, how do we categorize an acid? Is that it is a proton, proton, and remember protons are identified by H+. It is a proton donor. A base, therefore, is a proton acceptor. An example of what this can look like. We have HCl and NH3. We make NH4+ and Cl-. How you can go through and identify what's an acid and what's a base. An acid has a proton in which to donate. So here we have our acid, HCl. How do we know that's our acid? Well, if you go on the other side, that Cl is missing its proton. Therefore, this proton is being donated to NH3. And you can see on the reactant side that NH3 has an extra hydrogen, so that accepted the hydrogen, which makes our NH3 a base. What is unique about Bronsted-Lowry acids and bases is what's called a conjugate pairs, or conjugate acid-base pairs. So here we have a generic reaction. We have HA, which is our acid, and we have plus B, which is our base. HA loses its proton H and dissociates into an A-. B, the base, accepts that H to become HB+. So this is color coordinated for a reason. We have HA and A-. So HA and A- is what we call that conjugate acid-base pair. HA is our acid. A- is therefore what we call a conjugate base. This means in the reverse reaction, going back to reactants, A- is going to be the one accepting a proton to become its original acid, which is why we call it a conjugate base. So then we have B and HB+. That is our other pair. We know B is our base. Therefore, HB+ is our conjugate acid. Because it has that extra proton, it's going to be able to donate that proton back to A-, therefore it is an acid, but on the reactant side, in order to revert back to its original base form. Acids react to form bases, bases react to form acids, and vice versa, which is why we run an equilibrium reaction. As mentioned before, how do you identify these pairs? Well, an acid always has one more proton, or one proton more than its conjugate or its associated base, and the base has one less proton than its conjugate acid, so on and so forth. Here are a couple of examples we're going to work through. So we have an acid, CH3COOH. How do I know it's an acid? Is it has that H with it. And then we have H2O, in which we're mixing it with. So CH3COOH is going to donate an H to water. When that happens, our dissociated form of that acid, or the lost form, is CH3COO-. We take the H from COOH because that is a carboxylic acid. Therefore, it's an acid, and that's where we need to take the H from. Then we have our water accepting that hydrogen ion to become H3O+. Where are our pairs? Our pairs are CH3COOH and CH3COO-. Here we have our acid. here we have our conjugate base. H2O and H3O plus. Water's acting as a base, and here is its conjugate acid. Another example, NH3 ammonia is considered a weak base. It is reacting with H2O. So since NH3 is our base, water is going to be the one donating a proton. So we make NH4 plus, and that water loses that hydrogen to become O minus. What are these pairs? So we have NH3 and NH4 plus. NH3 is our base. NH4 plus is therefore our conjugate acid because it has one more proton than its associated on the other side. H2O and OH minus. H2O is our acid, and OH minus is our conjugate base because it has one less proton and will need to accept a proton back to turn back into an acid. Now, something you may have noticed here is that water is present in both, and in the first reaction it's acting as a base. In the second reaction it's acting as an acid. Well, water is one of these compounds that have the ability to work both sides of the equation, and we call this amphoteric or amphiprotic. That means it can act as an acid or it can act as a base. It has the ability to accept a proton or donate a proton as needed depending on what it works with. And that's kind of one of the unique properties that water has, and which is why it's really important for water in living systems, because it can work with acids and bases and neutralize and needs to occur what needs to occur in order to keep us safe. The second theory is the Lewis theory. Yes, Lewis dot structures. In bonding, he's come back again. And if you remember from Lewis dot structures, what we focus on in Lewis dot structures are those electrons. So he focuses on electron pairs. What he found the problem with the Bronsted-Lowry is Bronsted-Lowry focused on protons and only protons. But that didn't explain every interaction of an acid and base. It limited the view of what an acid could be. Therefore, Lewis went straight to the electrons, as the electrons are present everywhere and you can follow electron movement. And so he decided to create a much broader theory of what an acid-base pair can look like. A Lewis acid is an electron pair acceptor. A Lewis base is the electron pair donor. This definition has stayed the same because in order for a base to work in a Bronsted-Lowry, it has to have a lone pair in which to accept a positive proton. So that has stayed the same. It's this that has made a broader view, a Lewis acid. You don't necessarily need to have a proton for a Lewis acid to be an acid or have acidic properties. And so this is where the view has broadened on what an acid could potentially be. Here's an example of using a Bronsted-Lowry. Bronsted-Lowry, we have our proton and we have NH3. So this could have been HCl, it could have been water, whatever it happens to be. As you notice, ammonia has a lone pair of electrons in which to accept that positively charged proton to make NH4+. This could be considered both a Lewis acid-base combination or a Bronsted-Lowry acid-base combination. But if we're specifically going to look at Bronsted-Lowry and how Bronsted-Lowry gets a much larger viewpoint is this method. So we were never able to explain why BF3 has acidic properties. What happens is BF3 has what's called an incomplete valence shell. There are a few exceptions to the octet rule in making a Lewis structure. Remember, every atom wants to have a complete S2p6 valence shell, and that gives you a total of 8 valence electrons. There are some exceptions to this rule, specifically boron's family, and boron and aluminum. Even though aluminum is a metalloid, it does take on nonmetal properties. So we have this incomplete valence shell. It only has 6 valence electrons and not 8. So it has the ability to make 8. So when it comes into contact with ammonia, ammonia has a lone pair in which to donate to the cause to make sure boron has a complete octet. What does this look like? We have boron with its 3 Fs, nitrogen with its 3 Hs, and we have a bond between the two. Yes, this bond is an arrow pointing to where the electrons are moving. So nitrogen is donating those electrons to boron. We could call this bond a dative bond or a coordinate bond. Either works. But what it means is it's representing which atom is donating the electron pairs. So you know what is a base and what is the acid, especially for some of these more unfamiliar situations. That is one way a Lewis acid is different. The other way is vacant d orbitals. Up to this point, we have been working with all covalent compounds. We have noticed certain things occurring with ionic compounds. It's not really ionic compounds, it's just ions, specifically ions in the transition metals that carry some acidic properties that were not expected. The reason being is they have vacant d orbitals. What you have to remember with transition metals is transition metals are going to lose their 4s, 5s, 6s, 7s electrons before they lose any in their d orbital. And most of the time, most of the transition metals have relatively empty d orbitals, as you need 10 of them. Therefore, a transition metal can become a Lewis acid. A Lewis acid, therefore, is going to accept a lone pair of electrons from what's called a ligand. A ligand is the base. The 3 common ligands are water, cyanide, and ammonia. They all have lone pairs in which to donate to the cause. When you have a ligand and a Lewis acid, you create what's called a complex ion. You have discussed this back in topic 3 as well, looking at trends of complex ions on the periodic table. What does this look like? Well, you have copper and you have water. Specifically, copper makes attracts 6 waters in this particular complex ion. You can have different complex ions. This is just one example. So this Cu plus is attracted to 6 waters. Notice the coordinate bonds or dative bonds being represented, showing that water is the one donating an electron pair to copper. But this entire structure still has that +2 charge. As you can see, copper is carrying a +2 charge, which is why it's still considered an ion. But it's very complex, as you can see, that you do have Cu, H2O, and there's 6 of them, with a +2 charge as an ion itself. It is extremely complex, but it also represents that copper does have some acidic properties when put with one of these 3 ligands, and the only way in which we could explain it is the fact that there are electrons that are being donated to this complex ion, so on and so forth, that the Bronsted-Lowry theory does not necessarily account for. That being said, Bronsted-Lowry is the one we'll use most often, but just be able to recognize that these unique situations do happen, although they are rare.